Okay, so let's get started. Welcome back for some of you who haven't been here for a couple weeks. Just as a reminder of where we're going in this course, test number 1 is on Wednesday, September 18th. Please remember that there is a formula sheet that's available on the Graded Materials webpage that you can download prior to the exam to see what information will be given to you. This formula sheet contains both formulas and also our code. Also during the exam, please remember that you will be using these computers in the classroom to help you take the exam. Okay. Now since we're talking about these computers here, what I would like for all of you to do is to restart your computers. The reason being is because I discovered the first day of class that these computers were not did not have the latest version of R on it, and some other small updates were not actually installed that I had requested prior to the beginning of the semester. And so the Information Technology Services during the first week of class then installed the stuff here. But in order for all the updates to take hold, the computers need to be restarted. So please, all of you, restart your computers. If you see some computers that are near you where no one is sitting, please restart those as well. I would appreciate it. Oddly, before the semester started, the people on Information Technology Services had restarted all the computers to get all the updates on there, but for some reason they decided not to restart them again after they installed the new updates during the first week of school. Oh well, it's not that serious of a thing, but it would have been nice if they could have restarted it themselves. Okay. And so what we'll do next time to start class is just to verify that indeed all the updates did take hold on these computers. In addition, this also reminds me that since you will be taking the test with these computers, you should at least spend 5 minutes on these computers to familiarize yourself with what's available and where certain things are located. Because I would hate for you to ask, well, I shouldn't say I hate, I hope that you don't ask me, where is R on the computer right when we're starting to take the test, okay? So just, take some time over the next week and a half to familiarize yourself with what's available on these computers. So today we're going to start a section called Data, Distributions, and Correlation, for the lack of a better name for it. And this section will help us see some examples of the type of data that we will examine in this class. We will do some multivariate summary statistics. There's going to be a lot of review in this section, but there will be a few things that will be new to most of you. So while I guess I still think of this as background material, ideally this is how I would normally start the first day of class if we didn't have to do the introduction to R and also the matrix algebra introduction as well. So before we begin here, are there any questions? Okay. So
last time Sylvia asked for how to find the rank of a matrix.
Yes.
But can we use the eigenvalue to find the rank of a matrix? Like we have several eigenvalues and find the distinguished.
Find the what?
Find the distinguished one. Maybe there could be 5 eigenvalues, but
unfortunately, off the top of my head, I'm not 100% sure of the rule, but I believe it's the number of eigenvalues that are greater than 0 corresponds to the rank of a matrix. It's not going to be a big deal in our class, so that's why I don't go over it. But I believe that is the rule. If you really want to know if that's true or not, I recommend Googling it real quick. But really, it's not going to be typically an issue because where this rank issue is going to come up is when, for example, when we try to find an inverse of a matrix and it doesn't exist. Okay? Were there any other questions? Yes?
Can
speak up, please?
I can't log in, so
I'm sorry, I can't hear you.
I can't log in, so what do I speak to?
So you're using your regular old Blackboard ID and password?
Yeah,
You haven't been able to log in on any computers on campus?
I can log in.
But not on campus. Okay. Contact Information Technology Services and see if they can help you there. And if you have problems, let me know. Other questions? Okay. So, if you have a paper copy of your notes, please take them out. If not, hopefully you have an electronic version of the notes. So we're going to first take a look at 3 data sets that we're going to examine this semester. There will be more than 3 data sets, but this is these are some data sets that we'll spend a lot of time on, and they help motivate what we're doing. Also, before I forget, I'm only going to project on this screen from now on, not this one, because I don't know if any of you saw, if you watched any of the videos, there was a lot of distortion behind me with having two screens going at the same time, because it has to do with the capture rate, number of frames per second, not matching up on my on how I'm recording versus what's up there, and that was causing some distortion. So I'm only going to project up on one screen from now on. Okay, so again, we're going to take a look at 3 data sets. This first data set, some of you will be familiar with. If you took my STET 870 class last fall or STET 875 class in spring 2012, we talked about this data set, but we will examine the data set in a different way, mainly different ways in this particular class. So this is not going to be it's not going to be a duplication of what you've had in the past. And this is what I call my serial data set. Whenever I introduce an example, often you will see at the top here the name of the example, and then also you'll see some data files that are associated with the example, also some R files that are associated with the example as well. Okay, so whenever you go to a grocery store, you often see cereals arranged such as this. This is at my Hy-Vee at 27th and Superior. This is what it looks. That's what the cereal aisle looks like there. Where on one side of the aisle you see cereal boxes listed or shown there, and also notice how they're obviously arranged by shelves. And what I was curious about, or what I've been curious about in the past, is do grocery stores arrange the cereals in a certain way to, let's say, increase their sales? So, for example, maybe these grocery stores will put maybe high sugar content cereals on the bottom shelf. Let's call that shelf number 1. Or maybe the next shelf up, shelf number 2. So why do you think I mentioned high sugar content cereals?
Kids want high sugar cereals.
Exactly. Kids like high sugar content cereals, and if they're low on the shelves versus at the top, kids are more likely to see them and thus maybe more likely to pull them off the shelf and put them in mom and dad's basket. Now, as a non-scientific experiment or illustration of that, open this up again. I took my son, Callum. This was, I recorded this in November of 2011. He was 2.5 years old. Okay. And this is my oldest son. I thought I'd just turn him loose in the cereal aisle to see what would happen. Is my research hypothesis correct? I don't know. Well, we'll see what happens. I'm not going to give you the sound here, but I think it will be quite obvious what happens. So there's Callum. He's looking. Oh, there's Cheerios. Oh, who cares about Cheerios when you can have Cookie Crisp, a nice high sugar content cereal, and Cocoa Puffs. And why not do another one? And eventually I had to tell him, okay, that's enough. You've demonstrated the point. Interestingly, I went grocery shopping with my youngest son, Keegan, who's 1 year and 4 months old. I went grocery shopping with him yesterday afternoon at the new Super Saver in the Fallbrook area of Lincoln, Northwest Lincoln. And Keegan's in my cart. We're driving by the cereal aisle, and he goes, Elmo, 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 because there's some cereal there on the second shelf from the bottom that has Elmo on it, and he wants Elmo. I was a good father, and I did not put Elmo in my basket, but he wasn't very happy about that. So hopefully you were not shopping at that time at the Super Saver, and you might have heard some crying. Anyway, okay, so what I actually did a few years prior to this, I didn't actually collect my data from this Hy-Vee. I collected it from another grocery store. I actually did what's called a stratified random sample, where I stratified based upon the shelf. So shelf 1, the bottom shelf, I randomly selected 10 cereals. Shelf 2, I randomly selected 10 cereals. And hopefully, in a STAT 801-like class, you know how to randomly select or take a random sample. And that's essentially what I did, but I did it in a stratified manner. And this is what my data looked like. So, for example, the first shelf, the first cereal that I got was Kellogg's Razzle Dazzle Rice Krispies. It had a serving size of 28 grams. And what I was really concerned about in terms of, let's say, the nutritional content in the cereals was sugar, fat, and sodium. I'm interested in these 3 variables. Notice how I have 3 variables here. So this is called multivariate data. This first observation I have, what we often refer to this more so in statistics, is an experimental unit. An experimental unit is what the thing or object from which I am collecting my data upon. I'm collecting my data upon cereals, so that's the first experimental unit. Here's the second experimental unit, and so on. Okay? Now, so you can see I have a sample size of 40. There was only 4 shelves at this particular grocery store. And often in statistics, we have to worry about independence between, one observation to another. So do you think we have independence here between the experimental units? I hear some yeses. No. I hear some no's. I'm going to say no. Here's why. Let's go back to the data. We have a Kellogg's here. Oh, look, we also have another Kellogg's there. So it's made by the same manufacturer. So they might have the same kinds of practices of how they make these kinds of cereals. So do we have independence? No. But the reason why I bring this up is that, and some of you said, well, yes, we do, because look at how we are collecting our data. The reason why I bring this up is because there are going to be many situations in the real world where maybe independence isn't 100% satisfied, but we still treat it as independent. And we just hope that it's not going to affect our statistical analysis results. So it's, that, again, often happens in the real world. And in this particular class, we're going to assume that we have independence here. And the reason why, in case this wasn't clear, the reason why independence is important because it's often a mathematical assumption behind some statistical method that we use. So in order to do, let's say, a particular statistical method, we assume that we have a random sample from some population, which essentially means that I have independence between the different observations. Well, that's a mathematical assumption. In order to derive various things, that's what you need. But in a real-world situation, that might not necessarily happen. So again, what research questions may be of interest here? Well, are the nutritional contents in terms of, again, I only looked at sugar, fat, and sodium. The nutritional contents may be different. They differ amongst the shells. So, and we'll talk about that a little bit more as we go along. So here's another data set that we're going to be using this semester. It's a goblet data set. I first came across this data set a few months before I got married. And, before you get married, often what you do, you and your wife, you go to various stores and you register so that, you essentially tell these stores what gifts you want from the guests who come to your wedding. Personally, again, this is my opinion, not my wife's opinion. Personally, I think a wedding should be it's a celebration of, two people getting together, okay? And I don't want people to bring me gifts for that. I want all our guests to just come to a wedding and celebrate. But my wife, she wanted some gifts, okay? So one day we were at Dillard's registering and doing plates, glasses, spoons, all that good stuff. And I came across some goblets. And this was at the time that I had just started using this goblet data set in my multivariate course that I was teaching at the time. It's like, wow, I got some goblets, and there's some goblets here. And so I made my wife put down goblets on our registry. Unfortunately, though, no one bought us those goblets. But if you're interested, I'm sure you can still go to Dillard's and pick up exactly the goblets that we wanted. So anyway, so this is what a goblet looks like. These goblets in this data set were basically taken from an excavation site. So some archaeologists were digging in the dirt, and they came across some goblets, 25 different goblets they had, and they took a variety of different measurements in centimeters as shown there. So for example, x sub 3 represents the overall height of the goblet. X sub 1 represents the opening at the top of the goblet. And so this is what the data set looks like. It's a small data set, which is often good for illustration purposes. So for example, goblet number 1 had an opening of 13 centimeters at the very top of the goblet. And the subject matter researchers in this situation, meaning the archaeologists, were interested in coming up with some kind of grouping mechanism for these goblets. Just from looking at the goblets, so if you can imagine, let's say, all of them laid out on a table, it wasn't necessarily 100% obvious of a good way to, let's say, group them. Different goblets that are maybe the same in some qualities might correspond to certain uses of the goblets, or actually maybe certain time periods where the goblets could be used. And so from an archaeological standpoint, it might be good to somehow come up with a grouping of the goblets. And so we'll look at this data set more as we go along the semester and come up with groupings. And lastly, of these motivating data sets, we're going to look at what I call the place-kicking data set. And again, if you've had me for SET 875, you have seen this data set many times before, but don't worry, we will be using this data set in a different way. We are more interested in this particular example of prediction versus what we were doing in SET 875. And so this is a data set that I actually collected myself. It came across, or it came about when I was getting my master's degree in statistics from Kansas State. For the creative component of my degree, I had to do what was called a master's report. And what I did was I collected information on all place kicks that were attempted in the 1995 National Football League season. There was a lot. There was over 1,800 place kicks that were attempted. And as a kind of an interesting side note, this obviously 95 was about the time that that the World Wide Web really started started to take hold. People were really starting to use it. And this was the first time that basically every single play in the NFL, a description of what happened on that play was actually put on the internet. And so, I had a stack of papers about that high. I printed off all the play-by-play descriptions, stack of paper that high, looked through all the pieces of paper, and recorded about 1,800 place kicks. It took me about 40 hours to do. And so some of the information then I collected on every place kick that was attempted was such as, well, the week of the season, the distance of the place kick in yards, a variable called change, which basically, and we'll talk more about this later on, which basically was a measure of pressure. How much time's left to go in a particular half. Was the place kick what's called a point after touchdown or a field goal? In football, if you're not familiar, there are two different kinds of place kicks. Point after touchdowns worth 1 point if successful. Field goals worth 3 points if successful. Was the place kick attempted in a dome stadium or outdoor stadium? Was it a grass or artificial turf field? And was it windy or not when the place kick was attempted? My response variable is going to be called good, which basically was equal to a 1 if the place kick was a success, a 0 or a failure. 0 for a failure. And so this is what the data set that we will first be looking at looks like. This is actually about 80% of the observations that I collected. And so the first place kick, or you could say the first experimental unit, week 1, a distance of 21 yards. It was a change place kick. There was a lot of time left to go in that half. It was a field goal. I'm sorry. Yeah, it was a field goal. And we'll just keep on going here. And it was successful. Again, this is a multivariate data set because you can see here we have a lot of variables that we have information on. There's actually even more variables, but we're not going to deal with all of them in our class. So, what kinds of questions might be of interest here? Well, think of yourself in, I know this is college football, but think of yourself in Bo Pelini's shoes. If you could determine before a place kick was actually attempted, will it be a success or a failure, that then could be used as part of your judgment of, well, should I attempt this place kick or not? And so maybe with using data that we have on past place kicks, we can make a judgment. Will this be a success? Will this be a failure? And so that's the kind of thing that we're going to be looking at in this class for this particular data set. Overall, in these data sets, you've seen two different kinds of variables, continuous variables and discrete variables. Discrete simply means there's a finite number of possibilities, such as good, that good variable, success or failure, 2 possibilities. But then there's also continuous variables like time elapse. How much time's left to go in let's say, a particular half. Is it 24 minutes? Is it 24.5 minutes? Is it 24.55 minutes, or so on? In that case, a continuous variable, basically there's an infinite number of possible outcomes within a particular interval. Now, of course, we can't necessarily measure something to, let's say, an infinite amount of precision. So, for example, with the time elapsed, typically, you see 24 minutes and 30 seconds left. You don't see 24 minutes, 30.5, 6, 7, 8, 9, 10, or 10, 5, 6, 7 or so seconds left to go. So even though it is a continuous variable, we might measure it in a discrete sense and treat it essentially as continuous. The same thing with the distance of the place kick as well. 24 yards, 25 yards. You don't ever see, like if you're watching football yesterday, you didn't ever hear one of the announcers for a game say, this is going to be a 24.567 yard field goal. You don't see that. There's a limit to the precision that we measure some of this stuff. But we can still treat it as a continuous variable. Okay, so some of the topics that we'll be discussing this semester. We discussed this the first day of class, but I think it's still good to go over here. Now, again, just to help you now that you see 3 of our data sets, now so you can see what some of these topics are relative to potential data sets. So after we do this data distributions and correlations section, we will be talking about graphics. How do we, essentially look, have our data create a picture. So and we look at this picture to help make sense of the data. We'll do simple scatter plots, for example, but we'll look at other techniques such as trellis plots that help us look at multivariate data. If you think of it from this point of view, if you do a simple two-dimensional scatter plot, let's say x1 versus x2, well, you graph two variables. But what happens if you have 10? Well, it's hard to represent that in 2 dimensions. We'll look at ways that we can actually represent it in 2 dimensions and hopefully make sense of a data set. We'll be looking at principal component analysis and factor analysis. And again, this will help us try to make sense of a lot of variables and hopefully make sense in a way that's, or the theme, or the way that we will be doing is looking at trying to condense the data into a smaller dimension. In particular, for example, I got that out, obviously I did not. In particular, principal component analysis, what we'll be doing is this. Suppose we have, we'll say 10 variables. What we'll try to do is look at a particular linear combination of these variables. We'll call these variables x1 through x10. And we have some coefficients on this linear combination I just decided to call lambdas. And what we're hoping is that maybe through this linear combination, I could still get as much information from this data set that contains 10 variables. I could just get as much information by just looking at this linear combination. That's it. PC stands for principal component, by the way. But maybe one linear combination is not enough. Maybe instead, I have to do a second one. So I take a second linear combination. And these linear combinations that you'll see are chosen in a certain way that maximizes the amount of information that we can get from the data. Maybe I can just go with 2 linear combinations and hopefully make sense of essentially a 10-variant data set. Factor analysis does something very similar but not quite in the same way. And then we'll also be talking about cluster analysis, where what we're trying to do is you have a multivariate data set, imagine the goblet data set, and we're going to try to find natural groupings of the data. And that's what cluster analysis allows us to do. Often it's part of the same purpose of principal component analysis and factor analysis too, is to try to find natural groupings of the data. Once we get done with that, we'll take a test, and then we'll look at another section that focuses on prediction, where let's say beforehand, whatever experimental unit, a particular classification for that experimental unit, such as success or failure, as in the place-kicking data set, and now we want to predict that classification. And that's what these particular methods allow us to do. Something called discriminant analysis. This relies on a normality assumption for your data. Well, that may or may not be true. So for example, with the place-kicking data set, we saw one particular variable called type. That type variable was corresponding to, was it a dome stadium or outdoor stadium? So that's 2 levels. Do you think that's normal distribution? Do you think a normal distribution could characterize that? No. Okay, so this might cause us some problems. So we could look at something else called nearest neighbor analysis, which basically is what's called a non-parametric way of approaching the same kind of problem. The key is that since it's non-parametric, it doesn't make an underlying distributional assumption. We'll also look at logistic and multinomial regression models as well, with the sole purpose of prediction. And lastly, and then we'll take a test, and lastly, we'll look at some classical methods. If you would have took this course 20 years ago, you would have seen a lot of the focus of the course on these classical methods. I don't think it's necessary to do that anymore because there's a lot of other interesting things that we can look at that are very, very useful. We'll look at an extension of a regular t-test to a multivariate setting. We'll look at classical ANOVA methods extended to a multivariate setting as well. To give you an example of what might be of interest in a multivariate analysis of variance or ANOVA setting, consider the following. Now, with the serial data, I'm going to write this in an informal manner. You can imagine that for every observation, you could put their sugar value, you could put the fat value, and the sodium value into a 3x1 vector, right? Well, how about we let mu sub I be a 3x1 vector that represents the mean sugar, fat, and sodium content for shelf I. Okay? Then what we could do is this. Remember there was 4 shelves in this particular data set. Where now our null hypothesis is the mean vector for shelf 1 equal to the mean vector for shelf 2 all the way up to the mean vector for shelf 4. The alternative would be, well, at least one mean vector is not equal. That's what we would be interested in with that serial data, or one thing that we'd be interested in that serial data. This is multivariate analysis of variance because I have mean vectors versus just scalars that you would have had in an ANOVA setting. In fact, if you had me for setting 70, we looked at just sugar content alone, and we did the same hypothesis test. So we used regular old ANOVA methods. Okay. Any questions? So those are some motivating data sets for what we would be doing. We will be looking at other data sets throughout the semester. Not all of them will have stories behind them, but I find those 3 data sets interesting, so I thought I'd tell you some stories behind them today. So now let's put our data now into a more formal mathematical setting so that we can do statistics with it. So throughout the semester, we'll be using the following notation. P is always going to be the number of numerical variables of interest. So number of numerical variables of interest. Let's say you have a situation where you have a qualitative variable that has levels of A, B, and C. Well, what you got from another class before is to represent that in a data set, to represent that numerically, you would create 2 indicator variables for that. So while there's one qualitative variable, there's actually 2 indicator variables, and those 2 contribute to your overall P. Okay? Capital N is always going to be the number of experimental units or number of observations that we will have. At least in this class, an observation will be the same as an experimental unit. In a Stat 802 setting, you might talk about something a little bit differently, but that's what will be in this particular class. So capital N is always the number of experimental units. And we'll use a little x sub rj to denote the jth variable in the rth experimental unit. So indices such as like I and j will always be associated with variables. Indices such as r will always be associated with an observation or experimental unit. It's important to be consistent, so this is what I've chosen for this course. And what we're going to do is put all these x sub rj's then into a matrix that we will denote with a bold x. This is going to be called our data matrix. Okay? This is what the form of the data matrix looks like. So for example, x sub r11 represents the first observation for the first variable. X sub rp represents the first observation for the pth variable. X sub 21 represents the second observation for the first variable. So this is the structure of our data always. Again, the first indice always in a matrix corresponds to the rows. The second indice always corresponds to the columns. Notice also why I'm using R. Because R, that first index, represents row, as in R-O-W, row. Perhaps I should have used C for columns, but I didn't do that. Didn't think far enough ahead. So X is going to have a dimension of n by p. If we want to, we could just pull out one particular observation of interest. Let's call it X of R, represent our data in a vector. So this is an R by 1 vector. If we take the transpose of it, notice how I could then represent the transposes as each of the individual rows of our data matrix. Okay, so that's the setup. That's the notation that we use behind this. Just to make sure you follow this, let's take a look at the serial data put into this notational format. I'm going to look at the sugar, fat, and sodium, but I'm also going to include shelf in my data matrix as well. Now, before we can actually use the data, we actually need to make an adjustment to it. Let me go back to the original data set and split screen here. Okay. So, for example, observation number 1, serving size 28 grams. So, this is just comes from, let's say the side of the package that, shows what the serving size is, and there's 10 grams of sugar. Well, let's go down to Food Club Raisin Bran, observation 21. It has a serving size of 54 grams, and 17 grams of that is sugar. Okay. Does that mean then that Food Club Raisin Bran has a lot more sugar in it than Kellogg's Razzle Dazzle Rice Krispies? No. You have to take into account the serving size. So what I'm going to do is, for each of these variables, adjust them by the serving size. In other words, I'm going to take 10 divided by 28. Take 2 divided by 28, and so on. I'm going to do that for every variable. So for sugar and fat, you can see that, we'll look at the first observation, 35.71% of the serving size was just sugar for Kellogg's Razzle Dazzle Rice Krispies. 0 was fat. Well, that's good. There's no fat in it. This is healthy. You got to be careful, though, with sodium. I simply took the sodium value. I know I didn't say this before. Sodium is measured in milligrams. I simply took the milligrams value divided by the serving size in grams. And so that's why you see larger numbers here. If one wanted to, one could have converted the milligrams to grams for sodium and then divide by the serving size in grams. I didn't do it. It's not going to be meaningful to us. So that's why I didn't do it. So just be forewarned that's how I constructed the data. Okay. Yeah.
Is there any way to do that in R, like just take sugar divided by take sugar divided by the serving size using vectors?
Yeah, and we'll look at it. Yeah. So we'll get there. But thank you for the question. So in this case, I'm interested in sugar, fat, sodium, and also shelf. So P's equal to 4 in this particular case. Capital N's equal to 40. The first observation here, x11 would be 1, x12 would be 0.3571, and so on. I can put this into a nice little matrix form, and so here is my data matrix. I could look at, yes?
subset by row, it delivers the output as a column.
I'm sorry, say that again.
So I was wondering this earlier when we saw the generalized example.
Sure.
I see it again here, where you have the, on the next page, the x sub 1, and then it gives you the first row, but it delivers it to you as a
Okay.
column.
Yeah. It's just a matter of how I'm just arranging this stuff, and the problem is probably I shouldn't use the first subscript there for that, since I just have a vector. I don't need the first subscript, and so that's why you see this, this anomaly, I guess you could say, of the notation. Okay, so I apologize that obviously can be confusing, just we often think of our data in terms of row vectors. If you really wanted to, you could think of it as a column vector and make. I'm sorry, this is a column vector. We usually think of the data in column vectors. You can think of it as a row vector so that you wouldn't have this problem with the notation. So, yeah, I see your point, and maybe I'll make the change next year. Thank you. Okay, so that's our data format. Let's now move on to something called the multivariate normal distribution. All of you know about the univariate normal distribution. You see in your very first stat course, the old bell curve, the normal distribution. I'm going to call it the univariate normal distribution because you're only dealing with one variable in that particular case. Some notation. Let's just review the normal distribution. Suppose that I have a random variable x. Now, if I really wanted to, I could be formal, such as you would do in like a stat 882, stat 880, stat 883 class, and use a capital X to mean random variable. I am not going to do that here, since this is an applied class. It's not going to be a big deal for us if I just simply use lowercase letters. So the expected value of x, let's just call it mu. The variance of x, let's call it sigma squared. It's just a notation that we're using. Of course, remember, a variance, notice I'm saying var of x, is equivalently the expected value of x minus mu squared. So in other words, you're looking at, on average, how much does x deviate from the mean, and we're going to square it. Okay? We can represent this symbolically. Probably almost all of you probably have seen this notation before, as x and then a little tilde and mu sigma squared. That tilde, if you have not seen it before, represents the words is distributed as. So I would phrase this as x is distributed as a normal random variable with mean mu variance sigma squared. So with that then, the probability density function of x is this mathematical equation. And please note that there's a small error there. There should be a negative out in front of that stuff that's up in the power. If I see, well, before every one of my classes, I go through my lecture notes to prepare, obviously, for teaching. And if I see something as I'm going through where there's a typo or something, I would typically use a blue pen to denote it. I usually will remember to tell you that, yes, there was an error, please make the change, but if I don't, watch out for the blue pen marks in my notes. Okay, so this is the normal distribution. This is what's used to graph that bell curve. Of course, x goes from negative infinity to positive infinity. Notice I have a 1 over square root of 2 pi out in front. I have a sigma there. In other words, you can say it's the square root of sigma squared. And you take e raised to the negative x minus mu squared over 2 sigma squared. That's a univariate normal distribution, or the density itself. Well, let's look at a plot of it. This will help motivate then when we do plots of the multivariate normal distribution. Let's say that x is distributed as a normal random variable with mean 50 and a variance of 9, or 3 squared. And I want to graph this f of x. Okay? The quickest way to do that in R is to use what's called the curve function. This was discussed in this will be the second day of class, the introduction to R, where we use a curve function to put a regression line on a plot. Instead, now we're going to use the curve function to plot the normal distribution. But before we actually do the plotting, I think it's always helpful to look at a simpler example with the curve function. Let's say I want to graph f of x is equal to x squared. I want to graph it from x equal negative 2 to positive 4. So with the curve function in R, I can say curve. EXPR stands for expression. In other words, what do I want to graph? I want to graph x squared. Now, you always have to use the letter x there to say how I am varying, essentially, the values on my x-axis of my plot. So you always have to use x. So if you use a instead, well, this won't work. You'll get an error message. So you always have to use x. And then the x-axis limits, negative 2 to 4. And what R does, by default, it will put 101 values from negative 2 to positive 4, 101 values of x into x squared, get f of x out, and plot that then for the y-axis. So let's do that. And there's my simple plot. Okay. Now let's do this with the univariate normal distribution. Now what I could do is simply now put into our syntax this equation. I don't need to because actually in R there is a nice little function called dnorm. Density normal. That's where the name comes from. And what I can do is say I want my density of my normal to be evaluated at x with a mean of 50 and a standard deviation of 3. I want to evaluate it from 40 to 60. Why did I pick 40 to 60? Any ideas? It's about 3 standard deviations from the mean, essentially. It's a little bit more than 3 standard deviations, but it's pretty close. And we know that with the normal distribution, most of the probability underneath that curve should be within 3 standard deviations of the mean. Okay? So how about we make the curve red in color? Nice little label on the x-axis, a nice little label on the y-axis, and then a nice title to the overall plot. So if I run that code, there you can see my nice normal distribution centered at 50. The area underneath the curve is what? What's the area underneath this curve? Very, very close to 1. If I were to extend this out to negative infinity, positive infinity on the x-axis, I'd get 1, but then again, that would be hard for me to do exactly. So we'll just say the area underneath the curve is 1, because that represents probabilities. You could also just simply use the dnorm function like this, just to illustrate. Suppose I want to evaluate f of x for my normal density at 40, 50, and 60. And notice what I get. So at 50, I get a f of x of 0.132. And notice how that corresponds to what would be about the height, or that would, actually it is, the highest point of this curve there. At x equal 40, notice it's only 0.0005, and you can actually see that on the curve right there. Okay. So that's the univariate normal distribution. Should not be new to you other than maybe how to do this in R. Now let's talk about what's called the multivariate normal distribution. So now we're, instead of looking at just one variable at a time, we want to look at p different variables at a time and still have this normal distribution. So we're going to be looking at a vector. We're going to call it x. And notice how I correctly index it here with x1 through xp. So this is a column vector. And let's say that that has a multivariate normal distribution to it. Now before I can actually present the actual equation for the multivariate normal distribution, we need to make sure that you understand a few other items first. Okay, so here's the setup. Let's let expected value of x sub I be equal to mu sub I. So for the ith variable, it has a mean of simply mu sub I. Now, when you deal with more than one variable at a time, it's going to be very important to understand the relationships between the variables. And the way that we're going to measure the relationship, actually I guess you can say two ways. The first way is through what's called a covariance. I anticipate that most of you have seen covariances before, but I won't be surprised if some of you have not. So let's take a look at what a covariance is. Again, it's a measure of the relationship between two random variables. Our notation, we say cov, parentheses, xi, comma, xj in parentheses. So just like how you see bar of xi or spec or e of x of I, the same concept. And all this means in the notation is it's an expected value. So it's an expected value of how much your random variable deviates from its corresponding mean times then how much another random variable deviates from its mean. And this is going to be denoted symbolically, I know a lot of symbols today, by sigma sub ij. Very standard. This is what people use. So I did not invent this notation. Oops. Now we looked at the variance of x of I before. Again, as you learned in your first act course, that was an expected value of xi minus mu sub I squared. Now notice if I had the covariance of xi, that's going to be equal to the expected value of mu I. Oh, let's just do it over here. Running out of the room. It's going to be the covariance of xi is equal to the expected value of xi minus mu I times xi minus mu I. Of course, these two things are the same, and you get your variance. So the covariance of xi is just the variance of xi. That's the simplification. Also, it doesn't matter. Let me do some erasing. It does not matter which you do first here, if you work with the i's or the j's. It's like saying 2 times 3 is equal to 3 times 2. You get the same thing. So sigma sub ij will be equal to sigma sub ji as well. So again, covariance is a measure of association. If it's 0, no association. If it's greater than 0, it means that there's a positive association with it, meaning as x of I increases, you would expect x of j to increase. If it's a negative value, then it says as x of I increases, you would expect x of j to go down. Now the problem with the covariance is that there's no upper bound, no lower bound to it. And so what you did learn in your first stat course was something called, or what you learned about, was something called the correlation coefficient. And all that a correlation coefficient is again a measure of association, but now it's scaled so that it's between -1 and +1 always. 0 means no association, 1 means perfect positive association. -1 means perfect negative association. So in other words, and this is, if you could imagine, let's say you have your entire population, somehow you knew it. If I had something that looked like this, all my data values for x1 and x2, notice as x1 goes up, x2 goes up by exactly the same amount. This would correspond to row 1 sub 2 is equal to positive 1. If I did the same line, but now in a downward manner, that would be row sub 1, 2 is equal to negative 1. And lastly, just to make sure you follow this, if I did something like this instead, what would that be for row? Essentially probably 0. I mean, there's no association. I mean, as x1 changes, it doesn't look like you can necessarily predict what x2 would be. Now, the actual formula then for our correlation coefficient, and we'll denote the correlation coefficient by the Greek letter rho, R-H-O, is simply the covariance between the two variables divided by the square root of the variance of one of the variables times the variance of the other variable. That's it. So by doing that little dividing there, you end up forcing then this correlation always be between -1 and +1. Don't worry about a proof of that. So with that background then, we can put all these means, we can put all these covariances, we can put all these correlations into a matrix structure. So notice how I have a bolded mu here. This is going to be my mean vector. In other words, the expected value of my vector x. And the way that you work with expected values when you have a vector is you just simply put that expected value into all the components of the vector. So you can see it's just all my means, mu1 through mu sub p. If I had the expected value of some kind of matrix, all you do is you just move that expected value into every single element of the matrix and take the expected value of that single element. That's how you work with expected values. Suppose now I want the covariance of a random vector x. In case I didn't say this before, I apologize. This vector has random variables in it, so it's called a random vector. Okay. The covariance of x, then put into a multivariate format then, is the expected value of x minus mu times x minus mu transpose. Let's see if I want to do that yet. And if you go through multiplying everything out, you simply get all these covariances in a p by p matrix. Explain that a little bit more in about a minute. So what this means then is that sigma 1, 1, the row 1, column 1 element, is the covariance of x1 and x1, which in other words is the variance of x1. Sigma 1, 2 is the covariance of x1 and x2, and so on. Notice that what's always on the diagonal? The variances. Okay? The off-diagonal elements are the covariances. But also remember, sigma 1, 2 is equal to sigma 2, 1. Sigma 1p is equal to sigma p1. So what would happen if I took the transpose? Get the same. A covariance matrix is always symmetric. Perhaps this might be helpful for those of you who do not have much of a matrix algebra experience, but let's take a look at a case where we have p equal 2 and go through some of these matrix calculations that we saw within that expected value. So let's say that I want the covariance of x, where again it has two elements, x1 and x2. That's going to be equal to the expected value of, how do I write this? x1 minus, hold on, x1 and x2, that vector, minus the vector mu1, mu2. I'm going to run out of room here, so let me, hopefully you can erase as well. Putting some parentheses around doing that matrix or that vector subtraction. Then we're going to do x1, x2 minus mu1, mu2, transpose, and then the final parentheses. Okay, so that's what we need to do. We're going to go through this step by step by step. Okay. So this is equal to the expected value of x1 minus mu1, x2 minus mu2. Now that's one vector. Also, x1 minus mu1, x2 minus mu2, transpose, parentheses. Let's take the transpose now. So, expected value of x1 minus mu1, x2 minus mu2, x1 minus mu1, x2 minus mu2. So I have a 2 by 1 vector becomes a 1 by 2 vector because I'm taking the transpose. Let's do our multiplication. So expected value of, I have a 2 by 1 vector times a 1 by 2 vector. So what's going to happen in terms of what's the dimension of what I get as a result? The 2 by 2. So I take x1 minus mu1 times x1 minus mu1. So I'm taking the first row times the first column. Then I'm going to run out of room. X1 minus mu1. Draw a little arrow there. Sorry, I'm not planning very well in terms of room. X2 minus mu2. I'll just keep on going here. Hopefully that's readable. If it's not, let me know. Okay, so now I have a matrix, 2 by 2 matrix inside this expected value. So once I have that, then I can move this expected value essentially through to each individual element. When I do that, I'm getting the individual covariances. And thus, that's how I get my covariance matrix for a p equal 2 situation. Any questions? Okay. So then my correlation matrix then, in other words, the matrix that has all these correlations in it, looks like this. I simply, or let's say row 1, column 2, I put in the correlation between row 1, between x1 and x2. Notice that I have 1s on the diagonal. Why do I have 1s on the diagonal? Yeah, so the correlation between variable 1 and variable 1 is 1. They're perfectly correlated. So it's exactly the same thing. Also, row 1, 2 and row 2, 1. Are those equal or not equal? They're equal. Okay, so this matrix, then, as we saw with the covariance matrix, is symmetric. And we saw how these correlations came about. So that means if I know the covariance matrix, can I get the correlation matrix? Yes. Because everything that you need in that correlation matrix is contained in the covariance matrix. Okay. Let's look at how you can view this, how this covariance matrix comes about in a little bit of a different way. So, in your first stat course, you should have seen something like this, where the variance of xy, again, is equal to expected value of xy minus mu sub I squared. You could multiply the stuff out that's inside that expected value. So that's what I did. Let's call this step 2. I cannot write today. Sorry. So step 2 here, I simply multiplied everything out that was inside that expected value. Then, with this expected value, I can push it through any pluses and minuses. So that's step 3. So I have expected value of xy squared minus expected value of 2xi mu I plus expected value of mu I squared. Expected value of mu sub I squared is mu sub I squared. Why? It's a constant. Yeah, it's like saying, what's the expected value of 3? Well, it's 3. Okay, so this is a constant, so that's why I just have a mu sub I squared there. Mu sub I is a constant, so I factor it out. 2 is a constant, so I factor it out as well. So step 4, this is what my expression now looks like. Well, what's the expected value of xi? Well, it's just notation. It's mu sub I. So I have a mu sub I here, mu sub I here. So that means I have them squared. And then lastly, I combine this part and this part to get a negative mu sub I squared. So another way that you should have seen before to express the variance of xy in terms of expectations is expected value of xi squared minus mu sub I squared. Well, let's apply the same concept now to working with a covariance matrix. So again, it's just symbols. The uppercase letter sigma, in case I didn't say this before, I apologize if I did, is going to denote our covariance matrix. Another way to express it in terms of symbols is cov-x. Standard symbols that people use outside this course. So, what is the expected value? Let's call this step 2. Well, exactly what I gave it to you before. xi minus mu times x minus mu times x minus mu transpose. Now, step 3. I'm going to move this transpose inside my parentheses. It's just a nice little property that you can do when you're doing matrix algebra. You can move the transpose inside a parentheses such as this. If it doesn't make sense to you, what I recommend you do is just simply put in some simple vectors into R and try it yourself and see that you do get these two to be equivalent. Then, inside this expected value for, let's say, step 4, I can simply multiply everything out, just like what we had done up here when I multiplied everything out. So I get, let's see now, x times x prime minus x mu prime minus mu x prime plus mu prime. Okay. Now step 5. I'm going to combine these two things. Why can I combine them? I'm going to combine them into this 2x mu I. I'm sorry, 2x mu transpose. What's the dimension of x mu prime? X times mu prime. 1 by 1. Dimension of mu x prime. 1 by 1. If you actually look at the stuff multiplied out, you're multiplying exactly the same stuff out. So, because of that, I can simply combine that into 2x mu prime. Next, what I'm going to do is move my expectation through. So I have those 3 terms, and I have those 3 terms with the expected values next to them. Just like what we did before, I'm going to factor out my constants. So here's my constant, here's my constant. The expected value of mu prime. It's like saying what's the expected value of a number, like 3 again. So because of that, this expectation disappears. Expected value of x, that's just mu. So here's my mu right there. I combine some stuff, and this is another way to express your covariance matrix. That's built upon basically a multivariate extension. Do a different pen color here because I'm doing too much stuff with red. The bottom is the multivariate extension of what we saw towards the top. Just in matrix form. Just using some simple matrix algebra. Now there will be many times in this class where we have a main vector of 0. Maybe we did some stuff with our data so that we would have maybe we adjust our data so that we would have a mean 0. So notice what happens if I have a mean vector of 0. That part disappears, and I'm left with just simply expected value of x prime as my covariance matrix. This will pop up many times this semester. Okay, so we talked about sigma and p are symmetric. And that might be a good place to stop because then we will start talking about the multivariate. Are there any questions? Yes?
Will the x and p are both like p by 1?
Yeah, x is p by 1.
So x mu prime should be p by p, not 1 by 1.
Oh, yeah, did I misspeak? Yeah, I'm sorry. So x is p by 1. Mu prime would be 1 by p. So yeah, that should be p by p. In the end, the main thing, and sorry, thank you for bringing that up. The main thing is if you look at what's being multiplied, it's exactly the same. So at least I got that part right. But thank you for bringing that up. Other questions? Okay, so that's it for today.